Right, last one. Here we go. Here we go. So just before I start the last lecture, I want to emphasize something. So I left an exercise in the last lecture. It was that G is countable if and only if G countable, G is circularly orderable if and only if it embeds into homeo plus S1. And then we know from earlier that G is left orderable if and only if when you're countable, left orderable if and only if you embed in a homeo plus R. This is somehow kind of remarkable that these very combinatorial conditions completely classify countable groups that can act on one manifold. Right? I think this is worth saying. I think it's a really incredible thing. It's a purely combinatorial thing. Yeah, it tells you exactly when groups act on one manifold, at least orientation preservingly. Great. So last time we talked about, this morning we talked about bounded cohomology and how it can tell you more precise information about circular orderability. Okay. I think Steve's just going to watch from out there. And I want to continue along that path. All right. So the first proposition I'm going to talk about is rotation numbers. So something that I hinted at the end of last time. So suppose that you have F and G are circular orders on, or circular orderings on a group G. Is such that they are equal in bounded cohomology with interplay coefficients. Great. Then the rotation number with respect to G of any element A is equal to the rotation number with respect to F for all A and G. This is what I want to prove, just sort of straight from the definitions of what we had this morning. And I want to prove it today. You can really see where the boundedness is coming in. There's something very special about being boundedly cohomologous. I think is the right way to grammatically pass that property. And we know the converse is not true because Michele told us this morning. Converse is not true. You have examples where the rotation number of every element is 0, but the cohomology class is not 0. But here, proof. So we have for all A and B and G, if these two are equal here, that means that F of AB minus G of AB is equal to, I called it D in my notes, D of A plus D of B minus D of AB, right, for some bounded.
Sorry, I didn't understand very well the remark you made. So if F and G are secret orderings,
yeah,
then they may induce the same cyclic ordering. That's the point. So this morning you showed that there is an example of a cyclic ordering with the what was the statement you mean about the rotation number being 0?
So if you're a secret left ordering, your rotation number of every element is 0.
Yeah.
But the converse is not true.
Okay.
That's the remark I made. There's something isomorphic to that.
Okay.
Okay. Fine. Okay. Cool. So if you have two circular orderings which are boundedly cohomologous, that exactly means that this is true for some bounded function B from your group to Z. Okay, but it's bounded. So suppose the bound, so there's some minus M is less than or equal to D, let's just go less than, whatever, D of A is less than M, right, for all A, G. So let's fix some bound, right? This thing is bounded, so there is some bound. Fix it, call it big M. All right, now the first claim, the claim is that for any element A, right, N minus A respect to G. Okay, so the absolute value of the difference between these floors is less than n. Right. But this is true just simply because, right, the floor, notice the floor of MA, F is equal to n, and the floor of n minus d of A with respect to G is equal to n minus d of A. And this is, it's unwrapping the definitions of what the floor is with respect to each circular ordering. And you might be wondering what's going on with this n minus d of A. Where's that happening? Well, it's going to pop up a little later on in the proof. And it turns out that there's a map from sort of G tilde F to G tilde G, which is exactly this map, and it's an isomorphism. But we know that absolute value of d of A is less than. Now, let's actually compute the rotation numbers. Now define phi from G F tilde to G tilde phi NA is equal to n minus d of A. Okay, so here's an exercise. You can check that this is actually an isomorphism. Exercise is that phi is an isomorphism. So the group multiplication on G F tilde is determined by F. Group multiplication on G tilde is determined by G, and they're related by this function D. And this exactly allows you to translate between the groups. Let A be a group element in G, then our F and A. So I'm looking at the translation number of a lift of A, and I want to look at the difference between the translation number of the lifts. I'm going to pick a different lift here, n minus dA with respect to G. Okay, so I've got these two translation numbers, one with respect to F, one with respect to G. Let's unwrap the definitions here. So this is equal to the limit as k tends towards infinity of 1 over k and A to the power of k. This is with respect to F minus the floor of n minus dA A to the k with respect to G. But this is just equal to, so this is phi of n comma A, right? This is phi of n comma A. So this is the limit as k tends towards infinity of 1 on k and A to the k F minus phi of NA. I'm going to write it like this to the k. No, I'm not. I'm going to write it like that. Because it's an isomorphism, I can with respect to G. And then my lemma tells me, sorry, the claim here tells me that the difference between an element and phi of that element, the difference between the floors is always bounded above by m. So this difference is always bounded above by m. As k, it doesn't matter what k is, it's always at most m. Okay, so this means that the numerator is becoming really big, the denominator is staying the same. So this is just 0. Okay. So the translation numbers of these two lifts are equal. This implies that the rotation number with respect to F of A is equal to the rotation number with respect to G of A. I didn't even have to look mod Z because of the lifts that I chose. So rotation number is somehow a rotation number is an invariant of the cohomology class, bounded cohomology class. You actually get some kind of dynamical information out. Questions about that? All right, we're going to move on to the last part of the course, which is going to be all about taking direct products of circularly orderable groups. And we're going to pay close attention to the order of the cohomology class of your circular ordering. So far we sort of said, okay, you have a cohomology element. If it's 0 and H2, you can learn something about the group. The group's left orderable. If it's 0 and H2 bounded H2, sorry, then it's secretly a left ordering. Let's keep exploiting sort of kind of work out. If we have properties about the cohomology class, what can you tell about the group? That's what we're going to do for the last little bit. And the property of the cohomology class that we're going to pay attention to is the order. So order of cohomology classes. Let's see what we can learn from here. Okay, theorem. Let's just go straight into it. So this is a theorem. This appears in this kind of, so various forms of this theorem are known for a while, but the version I'm going to write down with the all the exact conditions and everything is due to Idris Abba and Play very recently. I don't know if it's been published yet, but no, it hasn't. Adam's shaking his head. Okay, so let's write it down. So suppose you have a group. Let this be a circularly ordered group. Circularly ordered group such that as a cocycle in H upper 2, not bounded. This has order n. This is an abelian group, so we can talk about, it's a group. You can talk about the order of some element. It just means n times f is the trivial cohomology class. Okay, has order n. Then there exists a K, which is a normal subgroup of G, such that G mod K is isomorphic to Z mod NZ, where this n is the order of the cohomology class. And K is left orderable. So I'm sort of telling you that if you have a cohomology class of a circular ordering which has order n, then there is a lexicographic circular ordering where the quotient is Z mod NZ. All right, let's prove it. One of the themes I wanted to get across in this course is that it pays to pay attention to the cohomology classes. It really pays to pay attention to cohomology classes and co-boundaries. And I'm hoping this is coming across. Here's another instance of this. All right, proof. And it's DAB. All right, so I'm just unwrapping the definition of what it means for F to have order n in cohomology. Is that there is some function D which satisfies this for all A and B. For all A and B in G. Great. Now let's let pi n from Z to Z mod NZ be the quotient map. Be the quotient map. Okay, how do I want to write this down? Then we have the following situation. I can look at pi n. I can look at D composed of pi n. Right, so pi n D of A plus pi n D of B minus pi n D of AB. Well, this is equal to pi n of F, of n times F AB, but this is just 0. So what have we learned is that this function D, the function D that turns n times F into a co-boundary actually gives you a homomorphism, Z mod n, right? This condition here, this being equal to 0 in Z mod n, exactly just tells you that this is a homomorphism. So pi n D from G to Z mod NZ is a homomorphism. Let's look at the kernel of this homomorphism. Let K be equal to the kernel of pi n times D, pi n of D. Okay. What is it? Let's unwrap it, right? It's all the G in your group such that n divides the G, right? Where n is an integer and dg is an integer, so I can talk about n dividing dg. So what I'm going to show is that when you restrict f, when you restrict the cocycle f to this subgroup K, you restrict it to K, what you get is actually that is the identity in H2 of K. So therefore K had to be left ordered. Okay, that's where we're going with this. All right, so let's define delta from K. Delta is going to be defined from K to Z by delta of G is equal to 1 on N times D of G, which I can define on K because K is exactly the things where N divides D of G. This is going to do the job for us. Okay, cool. So we have, for all A and B in K, we have that. How do I want to write this out? Right. Yeah, let's start from the delta. Delta A plus delta B minus delta AB. This is equal to N times D of A plus D of B minus D of AB.
And 1 over n.
I do mean 1 over N, thanks. 1 over N, thank you. Which is equal to this F, right? It's N times F divided by N, which is equal to F of AB. Beautiful. Right, what this tells us, so therefore, F, if I look at it inside H2 of K, right, is equal to 0. F is equal to 0 inside H2 of K with coefficients in it. There's a circular ordering on K, which is trivial in cohomology. That means K is left orderable. Let's leave that up there. So thus, K is LO. And there's one more step. You have to show that this map is actually surjective. Well, I'm just going to leave that as an exercise. That's not the main point of me proving this. So exercise is to show that pi n of D is surjective. And if it's not, you can contradict the order being n. So you go about it being surjective. I think this is really neat. Right? It tells you a lot about what's going on. Yeah.
If you take G visually figure, then it has H2 with coefficients in Q, which is 0. It satisfies this property. So you get exactly the result I was mentioning this morning.
Oh, thank you. That's very cool.
Can you repeat that, Ty, so I can hear it?
So
If you take the figure, then it has H2 with coefficients in Q, which is 0.
Oh.
It is a classification, it's virtually cohomological dimension 1. It's virtually free.
So then you know that the H upper 2 has torsion. It's
Exactly.
it's
Yes.
completely torsion. So any circular ordering has finite order. Yeah.
So you get this
So you get
finite cyclic quotient, and the K is a subgroup which is torsion free, so it must be free.
yeah, good. That's neat. Great. Okay.
Wait, sorry. Oh, go ahead. Go on.
Now remember when we were talking about trivial cohomology classes, if a class is trivial, if a circular ordering has trivial cohomology class, that means the group is left orderable. If a class is trivial in bounded cohomology, that means that is a left order. So bounded cohomology tells you more. Here's an exercise. You can flex your playing with cocycles muscles. Well developed. We've got show. So GF circularly ordered group. If F has order n in bounded cohomology, then F is lexicographic with respect to 1, okay, to G to Z mod N. Okay, so bounded cohomology tells you how to identify that order. Not only that the one exists, a regular cohomology tells you one exists, bounded cohomology tells you it's that one. How are we doing? Good, we are doing well. Okay. Let's finish up by talking about direct sums. So, infuriating open problem. B and H are CO when is G cross H CO. If they're both left orderable, that's true. It's kind of silly. But let's restrict our attention just to start to direct sums of direct products with finite cyclic groups. Just to get warm. Because here you can actually say something, it turns out. Okay. So another question is, G is CO. What about G cross Z mod NZ? When is that circularly ordered? All right, let's prove some, let's just make some observations first. Okay. If Z mod MZ is a subgroup of G, and the GCD of M and N is not 1, then you're going to be in trouble. And the GCD of N and M is not equal 1, then G cross Z mod NZ is not CO. Why? Because inside here, you'll have something of the form. Let me just write it down. Since Z mod GCD of N and M, Z squared will live as a subgroup of G cross Z mod N. And this is not circularly orderable. That's not going to be circularly orderable. Okay, so somehow the existence of torsion will be your first place to go to obstruct these things to be circularly orderable. However, torsion is not sufficient to obstruct. Let's return to our good friend, the Promislov group, that Adam spoke about not so long ago. Example, G, the Promislov group. There's nothing this group can't do, right? It's the counterexample to the Lansky unit conjecture, and then it's torsion free, not left orderable, but it is circularly orderable. It's great. It's a good group. All right, so let me write down some facts about it. So G is torsion free.
We call that a bad group in geometric group theory.
G is torsion free and not LO, but it fits into a short exact sequence. 1 goes to Z squared semi-direct product Z, the G to Z mod 2Z to 1. This is LO, this is CO, this is CO. So G is circularly orderable. And also, I'm not going to prove any of these facts. I just want to show you that there's examples of things that are not obvious. All right. Also, G cross Z mod NZ is CO if and only if 4 does not divide N. I mean, not once it's written down and Adam's told you how to do it. No. I don't think I could have done it myself. You play with the presentation that Adam gave you, you build a bunch of homomorphisms.
Fiddle around till it happens.
Yeah.
It's nothing deep.
I think the hard thing about it is knowing that something like this can be true, right? I think this is once you know that something like this is true, then you could probably prove it. Anyway, short answer is yes for me. Definitely, it's hard. Okay, so weird things can happen, right? What's going on? What's actually going on here? The way I'm going to think about these, G cross Z mod NZs, or more generally, circularly orderable groups with a finite cyclic subgroup, is that you remember when we took our circular ordering and then we looked at this infinite, universal cover, Right, this was G, and then this was G tilde F. And where there's the identity. And then we took, the picture was you took copies of the group, unwrapped it, glued them together. And that's the universal cover of R over S1. You might know that there are other covers of S1. They're of S1 over itself. But you can absolutely imitate that whole picture in the world of circularly orderable groups. So somewhere in between here and here, you can create a circularly orderable extension by a finite cyclic subgroup. And I'm going to call this G F tilde N. Where this is some, and what's going on here is that you have one going to Z mod NZ, going to G tilde N, F, going to G, going to 1. Right, so instead of completely unwrapping, you unwrap to an intermediary cover, finite sheeted cover. And how do you play this game? Instead of looking at homology with coefficients in Z, sorry, cohomology with coefficients in Z, you look at cohomology with coefficients in Z mod NZ.
What do you write that? What about the product of the promised law itself?
It's circularly orderable. The reason we check that is because you asked me this.
Getting old.
So you asked me this in like 2021 or something. Yeah. And I bet this is true. Actually, it was 2020.
2021, we know about that.
Beginning of 2020. That's right. Yeah. Because I asked this sort of question. I gave a talk in McGill, and then he said conjecture. No, he didn't say conjecture. He said, what about?
Conjecture, I said conjecture.
Okay, conjecture. Sure. I don't want to throw you under the bus. It's a good conjecture, and it's like ought to be true, except for the fact that it's not, which is really unfortunate. Is that G is, so take a circularly orderable group. G is left orderable if and only if G cross G is circularly orderable. I think this is what you more or less said. Anyway, that turns out to be false, because a Promislov group, you can take its square and it's still circularly orderable, but you can also show that if you keep going, there's some number after which it stops becoming circular. It's not 2. I think we've got some bound on it, right?
It's bigger than 3 or something like that.
Yeah, but it's finite.
Yeah, so eventually it fails.
Yeah, and it relies on it being amenable, right? So I'm trying to remember how this proof goes. Yeah, it's weird. It's a wonderful world to be in, though, right?
So can you upgrade the conjecture to taking the products? That's probably where you.
Yeah, feel free. That, yeah. I'll write that down tomorrow in the problems. I think I just don't know what's going to be true. Sorry, this is where I was. Okay, but focusing on finite cyclic covers, at least, sorry, finite cyclic subgroups, or direct products with finite cyclic groups. They're going to fit into central extensions like this, except instead of the kernel being Z, it's Z mod N. So we want to pay attention to F, so a circular ordering, but inside H2 of G with coefficients in Z mod NZ. This is where you want to pay attention if you want to look at, if you want to ask a question about direct products with finite cyclic groups. Here's what you want to, and here's the theorem. The whole story with Z just flows through nicely. If you use this idea that these really are intermediary covers from some universal covering space, then you can prove all the same kinds of theorems as we had before. And in fact, one of them is that oh, sorry, let me write down a bit more than just saying everything runs through. Apologies, I got a bit excited and then lost my spot in my notes. All right, so the first exercise is that, F, a circular ordering on G, CO on G, F in H2, Z mod NZ, defines a central extension just because of the correspondence between H2 and central extensions. When I wrote down that correspondence, I had Z here, but you can do everything where I replace Z with Z mod N. Okay, so this defines a central extension, 1 Z mod NZ to G F tilde N to G to 1. So the exercise is that G F N tilde is circularly orderable. That's the first thing you can show. How do you do it? Go right up to the universal cover. And when you quotient back down, instead of quotienting by the cofinal central element, quotient by 5 times the cofinal central element, 7 times, or n times. Then you get a circular order. All right, so conversely, given a normal subgroup, Z mod NZ, normal inside G, where G is CO, we have a central extension. Extension 1 goes to Z mod NZ, goes to G, goes to G mod Z mod NZ. Goes to 1. And you might object and say, I only said that this was normal. But I think this morning, or maybe yesterday, we proved that if you have a normal finite cyclic subgroup, it's actually central. So you take a normal subgroup in here, it's actually central, so you get this central extension. And following in a similar vein to the case with Z extensions, you can prove exercise is that G mod Z mod NZ is circularly ordered. This is actually kind of an interesting statement, is that if you have a circularly orderable group with a normal finite cyclic subgroup, you can quotient by it always and still be circularly orderable. So if you believe these two exercises, it's not too much of a stretch of the imagination that you would get the following theorem. B circularly orderable, G cross NZ, Z mod NZ is circularly orderable if and only if there exists a circular ordering F on G such that F is 0 in cohomology with cyclic coefficients, the Z mod NZ. Because you take the central extension, and then this is actually G cross Z mod NZ. And one of the exercises to prove it's circularly orderable. If and only if. So this is true, and then there's an equivalent way to formulate this being true, is that if and only if there exists a mu in H2, G with Z coefficients, such that N mu equals F in H2 with Z coefficients. So F is divisible by N. And before we talked about the order, now we're talking about divisibility of the cohomology class. The questions about this setup so far? Let's see what we can get out of it. Shall we? All right, corollaries. E a circularly orderable group and H2 of G with Z has finite exponent. So that means E times every element is trivial. In particular, maybe this is a finite group, which happens if you care about rational homology 3 spheres, for example. Which you might, some people might. There's some big conjecture. Okay. Here's what you can say. If the GCD of NE is equal to 1, then G cross Z mod NZ is CO. Let's get that around the wrong way. This is exactly because if you have an element, a non-trivial element in this, it's always n divisible when the GCD is 1. This is a group theory exercise. Finite exponent means that, let me write it here. It just means that like S times E, E times mu is equal to 0 for all mu in your group. The other corollary you get is that if G is not LO, then G cross Z mod NZ. Sorry, Z mod EZ is what I want to write down. Is not CO. If you're not left orderable, that means there is no circular ordering that lives in the identity in here, that lives in the trivial cohomology class. So now there are no non-trivial elements that are divisible by E, because the exponent's E. Okay, so this is direct products with finite cyclic groups. And I just want to maybe tell you about a theorem that says you should focus on these guys. All right, it's G times Z mod NZ. So here's a theorem. It's due to Jason Bell, Adam Clay, myself, from a couple of years ago. A group G is left orderable if and only if G cross Z mod NZ is circularly orderable for all n. I guess for all n greater than or equal to 1. Let's just go with the natural numbers. I'm not going to sketch out the proof, but I want to talk about some new sort of objects you get out of this theorem. Okay, so somehow taking direct products with every finite cyclic group means you can completely be unwrapped. I don't quite know how to interpret this intuitively. It's a circularly orderable group, as long as you can take a direct product with arbitrarily large finite cyclic groups and still be circularly orderable, then you're actually left orderable to start with. Only way this can happen.
So the statement arbitrarily large, or
no, all of them. Yeah, I really need all of them.
Okay.
Sorry, I was trying to wave my hands and I waved them too hard and fell off. Okay. Okay, so with this in mind, we can make a definition. So let G be CO. Oh, by the way, before we do that, so I had the Promisloff group up before, right? It's circularly orderable. And when you take the direct product with a multiple of 4, a cyclic group of size with a multiple of 4, it's not circularly orderable, but all the rest are. So somehow it's the cyclic groups of order 4 that are making this thing not left orderable. But with that in mind, let's talk about the set of ends which stop a group from being left orderable. And that's going to be called the obstruction spectrum. So let G be circularly orderable. Define the obstruction spectrum of G to be OBG, which is equal to set of all natural numbers that obstruct G from being left orderable, such that G cross Z mod NZ is not CO. First exercise. K is in the obstruction spectrum. K times the natural numbers is a subset. Obstruction spectrum. This is simply because Z mod KZ is a subgroup of Z mod K times TZ. For all natural numbers T. There are examples of groups torsion-free groups such that, all right, so there are examples where the obstruction spectrum of G is equal to everything, like circularly orderable groups, where this is true. There are examples where this is true, where P is prime for all primes. And there are examples like the Promisloff group where you can get things that aren't just multiples of primes. And it's not clear at all which subgroups which subsets of the natural numbers can appear as obstruction spectrums in circularly orderable groups? Question. Which subsets of n can appear as the obstruction spectrum of some group? Here as
An example where it's not a cyclic semigroup.
where it's not a cyclic semigroup. Yeah, there are examples where you have like, you can take, I think we have torsion-free examples of this. You can take S be any subset of the set of primes. Take a favorite subset of the set of primes. And then we have examples where the obstruction spectrum is, I guess, the union of the primes in S of P times N. Yeah, and I guess this isn't a cyclic semigroup.
Well, you could include one, couldn't you?
No, because it's a circularly orderable group. So G cross nothing is circularly orderable here. Yeah. So I'm gonna stop there. That's plenty.
Last example, was it any S I hand you, or there are some S that?
No, any set, any S. So you can construct these with torsion groups. Like if you take take your favorite subset S, and then take the cyclic group Z mod, product of all the primes in S. Z. That will have obstruction spectrum exactly this.
If G and H have like sort of compatible obstruction spectra, is there a hope that their product would be?
That's what we would have liked to have proved, but here's an example that shows you that there's no hope whatsoever. Just forget. That's not true. I mean, maybe there's something more subtle you can do. But G, the promised love group, the obstruction spectrum of G is 4n.
Oh, I see, but
Obstruction spectrum of Z mod 2Z is 2n. Obstruction spectrum of Z mod 4Z is also 2n. But I've already got it written up there in disguise. But here's what's true is that G cross Z mod 2Z is CO. G cross Z mod 4Z is not. But maybe this tells you need more information than just the obstruction spectrum to get something about direct products.
what if they were co-prime or something? Would that be good or bad?
It might be better. I mean, I'm assuming the intuition, where the intuition is coming from is that if you look at finite cyclic groups, right, the direct product is going to be circularly orderable exactly when sort of the divisors are disjoint, which is exactly the generators of their obstruction spectra. Well, no. It'd be great to prove something about something here.
What are the obstruction sets of the products of the group itself?
Oh, don't know.
Eventually, everything.
Eventually. Yeah, don't know. Obstruction spectrums play nicely. So like with free products. So if you have a free product of two circularly orderable groups, the obstruction spectrum is the union of the two.
Oh, that's where this is.
We proved this, yeah. But that's the only sort of nice property, non-trivial property besides maybe observing that this is true. So, yeah.
The definition of obstruction spectrum, if you only ask the G group is left orderable, can you make the same definition, and or is it just?
So if you're left orderable, then G cross Z mod N. I mean, do you want?
I want it to be still circularly orderable in the end. So like the set such that G cross Z1N is not circularly.
Well, if G is left orderable, then you can lexicographically circularly order every direct.
Okay.
On the dark, is the obstruction spectrum tell you what quotients of a group might be LO?
What quotients might be LO?
Yeah.
I don't know. I doubt it.
Like just the fact that OB of Promislov is 4n tell you?
I wouldn't know how to approach, yeah, something like that. Yeah, all right, let's go.